Okay, welcome back, Chemistry 30. So I left you with B and C to do here. An endothermic process absorbs 138 kilojoules. How many calories is this? So if we take a look here, we're going from kilojoules to joules, and then from there we can use this conversion factor here to figure out how many calories it is. As a side note here, endothermic means absorbing, so the system or the reactants absorb energy to produce products. So we kind of think of that as being positive energy. We're receiving it. So to figure this out, changing to joules first of all, 1 kilojoule is 1,000 joules. So kilojoules cancel. If I was to stop right here, my answer would be in terms of joules. But of course I want to go from joules to calories. So I'm going to be using this conversion factor here, except flipped over because I want joules on the bottom. So I can cancel out joules and calories on top. So I get 3.30 times 10 to the 4 calories. And that's, again here, if I set these conversions up or figure out what I'm converting first of all, so do something like this, figure out what the conversion is, and then from there, set them up. The next question is very similar, except this time it says an exothermic reaction releases 325,000 scientific calories. Convert this into kilojoules. So exo means released. When reactants form products, energy is released because it's not required, it's not needed. So again here, we're going from calories to kilojoules. So first of all, we have to convert to joules first of all. So we're going to be using this conversion factor again. Now notice, we think of exothermic reactions as negative energy, negative amounts of heat, because we're losing it. It's being released. So negative 325,000, 1 calorie is 4.184 joules. So if I was to stop the question right now, I'd have it in joules. But of course I want to go one more step, change it to kilojoules, and I know that 1 kilojoule is 1,000 joules. So there we go, we have that conversion. So you get negative 1,359.8 kilojoules when you figure that out. In terms of sig figs, I have 3 sig figs, so keep the 1, keep 3, keep the 5. This is a 9, so that gets bumped to a 6. And I have that 0 as a placeholder, or I can write it in scientific notation. Negative 1.36 times 10 to the 3. Okay, so specific heat, we kind of touched on that. For the definition of a calorie, we're looking at the specific heat of water, the amount of energy required to raise the temperature of 1 gram of liquid water by 1 degree C. But if I'm just looking at specific heat in general of a substance, it's the amount of heat required to raise 1 gram of whatever substance it is by 1 degree C. And of course, every substance has a different value because its composition is different. Iron, for example, is different than water. It's much easier to heat up iron than water. Water is considered to have a large specific heat value, so it can absorb release large amounts of energy. The reason being is that hydrogen bonding holds water molecules close together, and we require much heat in order to separate those that hold that those hydrogen bonds have. Okay, kind of a neat thing here is why using this idea that water has a huge specific heat value. Why would it make sense to make plant life next to large bodies of water, or orchards next to large bodies of water? The reason being is that during a hot summer day, the water would absorb a lot of heat. And then if it cools off in the evening, of course the air is going to be cooler than the water, so the water releases that heat, and anything nearby will have a warming effect. So when it gets cold outside, water releases the heat that it has, and it keeps the plant life or trees warm, and may even prevent freezing from happening. Next, so using specific heats, which we symbolize as C, of course, C represents so many joules per gram degree C, or if we look here on the handout I gave you, we have different specific heats of substances. So Water has 3 different values depending upon the state it's in. Aluminum, granite, etc. So you can see the amount of heat, joules, for every gram degree C. For every 1 gram to move by 1 degree C, this is how many joules it takes. So if we take that number, and of course we may not necessarily have 1 gram of it, so we multiply by m, and of course instead of looking at just a change of 1 degree C, we may be looking for another change, so delta T. So you see how the units work out here, joules per gram degree C times grams times degree C, so that gives us a value of joules. So Q is heat, C is specific heat, M is mass, and delta T is change in temperature, which is final temperature minus initial temperature. Okay, so if we're looking at, let's say, how many joules of heat are lost by a 3,580 kilogram granite rock as it cools from 41.2 degrees C down to negative 12.9 degrees C. So writing down the information that we know, we're looking for Q, and if I look back at this sheet here, granite, 0.803 joules per gram degree C, that's where I got that. Mass, it's in kilograms, I have to change it back to grams, so multiply by 1,000 G's over 1 kilogram to get that, 3,580,000 grams. And then be careful with the temperature here. You identify the starting temperature, the final temperature, and it's always final minus initial. Even if you know you're going to get a negative, that's okay. So my final temperature, negative 12.9. Subtract positive 41.2 degrees, and I get negative 54.1 degrees C. So then substituting that into the equation, my specific heat of granite multiplied by the mass of granite multiplied by the temperature change, and I see I get a negative number here, which makes sense because the heat is being lost by granite. It's cooling down, so it's releasing that heat. So the granite itself is experiencing a negative heat, it's losing it. 1.56 times 10 to the 8 joules. Okay. I'll have you try the second one here, B, and then we'll look at the next video to see how you make out. See you shortly.